So an easy example now. So of course the elementary examples are coins, cards, dice. So let's deal with dice, but to keep the diagram small, instead of a six-sided die, we're going to think about a die that only has 4 faces. So you can do that with a tetrahedron, it doesn't really matter. Basically, it's a die that when you roll it, you get a result which is 1, 2, 3, or 4. However, the experiment that I'm going to think about will consist of 2 rolls of a die. Crucial point here. I'm rolling the die twice, but I'm thinking of this as just one experiment, not 2 different experiments, not a repetition of twice of the same experiment. So it's one big experiment. During that big experiment, various things will happen, such as I'm rolling the die once, and then I'm rolling the die twice. Okay. So what's the sample space for that experiment? Well, the sample space consists of the possible outcomes. One possible outcome is that your first roll resulted in 2 and the second roll resulted in 3, in which case the outcome that you get is this one, a 2 followed by 3. This is one possible outcome. The way I'm describing things, this outcome is to be distinguished from this outcome here, where a 3 is followed by 2. If you're playing backgammon, it doesn't matter which one of the 2 happened. But if you're dealing with a probabilistic model that wants to keep track of everything that happens in this composite experiment, there are good reasons for distinguishing between these 2 outcomes. I mean, when this happens, it's definitely something different from that happening. A 2 followed by a 3 is different from a 3 followed by a 2. So this is the correct sample space for this experiment where we roll the die twice. It has a total of 16 elements, and it's, of course, a finite set. Sometimes, instead of describing sample spaces in terms of lists or sets or diagrams of this kind, it's useful to describe the experiment in some sequential way. Whenever you have an experiment that consists of multiple stages, it might be useful, at least visually, to give a diagram that shows you how those stages evolve. And that's what we do by using a sequential description or a tree-based description, by drawing a tree of the possible evolutions during our experiment. So in this tree, I'm thinking of a first stage in which I roll the first die, and there are 4 possible results, 1, 2, 3, and 4. And given what happened in the first, let's say in the first roll, suppose I got a 1, then I'm rolling the second die, and there are 4 possibilities for what may happen to the second die, and the possible results are 1, 2, 3, and 4 again. So what's the relation between the 2 diagrams? Well, for example, the outcome 2 followed by 3 corresponds to this path on the tree. So this path corresponds to 2 followed by a 3. Any path is associated to a particular outcome. Any outcome is associated to a particular path. And instead of paths, you may want to think in terms of the leaves of this diagram. Same thing. Think of each one of the leaves as being one possible outcome. And of course, we have 16 outcomes here. We have 16 outcomes here. Maybe you noticed a subtlety that I used in my language. I said I roll the first die, and the result that I get is a 2. I didn't use the word outcome. I want to reserve the word outcome to mean the overall outcome at the end of the overall experiment. So 2, 3 is the outcome of the experiment. The experiment consisted of stages. 2 was the result in the first stage, 3 was the result in the second stage. You put all those results together and you get your outcome. Okay, perhaps we are splitting hairs here, but it's useful to keep the concepts right.